Hello, in this chapter we're going to talk about motion in 2 dimensions, which is a continuation to what we talked about in the previous chapter, motion in 1 dimension. However, we're going to generalize what we learned about velocity and acceleration to more than 1 dimension. First, we want to start by distinguishing between scalars and vectors. So scalars are the physical quantities that can be specified only by a single number. So for example, mass, the mass of an object is just given by a number. So if I take a kilogram, 1 kilogram of potatoes, that's just a number. The number of moles inside a sample that I take, that's only a number. I only need a number to specify the volume, temperature. All these called scalar quantities. However, some quantities in physics, it's not enough to know their value, to know everything about them. We need also a direction. So vectors are the physical quantities that have direction in space. So we need to know their direction in order to know everything about them. For example, position, displacement, velocity, forces, all these quantities are vector quantities. And in order to distinguish between vector quantities and physical and the scalar quantities, we put a small arrow on top of a vector quantity. So if we see an arrow on top of a symbol, that means it's a vector quantity. We have to be careful while we're dealing with vector quantities because we cannot add or subtract vector quantities as we do in scalar quantities, because we have to worry about the direction. Because depending on the direction, these quantities can be added or subtracted. Sometimes we can write what we call vector equations, and we have to distinguish between those and scalar equations. And we cannot write an equation that add or subtract vectors from scalars. So scalars and vectors have to be distinguished from each other. Now, each vector has a magnitude, and the magnitude of the vector is a scalar, and I can deal with it as a scalar. What is the magnitude of the quantity is how strong this vector is. So it's the magnitude of the quantity vector. Okay, the first vector we want to describe is the position vector. So if we want to describe the position of an object, we start as usual by choosing a reference point. So for example here, if we want to describe an object on a table, we choose the reference point as one of the corners of the table. Then the position vector is going to be an arrow starting at the origin or at the reference point, pointing toward the direction of the object on the table. The tip of the arrow would be the position of the object. Now, how can we describe this vector? First, again, we need to choose what we call positive direction. So here it's not enough to choose one direction, we need to choose 2 directions. So if we go back to the example of the table, we choose one of the edges and we call it the x-axis, and the other edge we call it the y-axis, and we choose a direction in which we go. It has positive on the x-axis and positive on the y-axis. Now, in order to specify exactly where this object is on the table relative to the reference point, we need not only one number, we need 2 numbers, x and y. So x and y are the coordinates of the position. The x would describe how far we are on the x-axis, and y would describe how far we are on the y-axis. The position vector, we refer to it as r vector with an arrow on top to indicate that it is a vector, and then it's equal to x and y. So x is the distance on the x-axis and y is the distance on the y-axis. Now, another way to describe this vector is we describe the net distance from the origin, and this is we call the magnitude of the vector or the magnitude of the position vector. So it's the distance, the absolute distance from the origin, and then we describe or we calculate the angle with one of the known axes. So here we have the angle with the x-axis, we call it theta, and then the distance from 0 or from the origin to where the object is r without a vector. So this is a magnitude, it doesn't have a vector. The relation between these 2 notation, r is equal to the square root of x squared plus y squared. This comes from Pythagoras theorem because the Cartesian coordinate is always a right angle, and the x coordinate is related to the magnitude of r, multiplied by cosine theta, and the y component is r sine theta. We used cosine for x and sine for y because in this example we took x as, the way we measure theta is with the x-axis. So x is the adjacent and y is the opposite. The second important vector we need to discuss is obviously, of course, the displacement vector. So again, motion is the change in position. So in order to have motion, we need to have change in position. So we need to describe the displacement. So as vector, we write delta r vector is equal to the final position r vector minus the initial position r0 vector. So here on the figure, you see here again, we go back to our Cartesian coordinate. We have the reference point, the origin. The object was initially at this position here. So this is the initial position. It's described by an x and y, x initial and y initial, or x0 and y0. And then the object moves to the final position r, where we have x final or x and y. So the displacement is also a vector, and it also has two components. It has a component where we went parallel to the x-axis a little bit and then parallel to the y-axis. So that's our displacement. So it goes here and then it goes straight up here, and that's the gray displacement vector. And in components, I can directly write the change in x, or delta x, is equal to x minus x0, and delta y is y minus y0. If we want to find the magnitude of the displacement, delta r is going to be delta x squared plus delta y squared. After the position and displacement, we will define the average velocity, or the velocity. So the velocity is defined as the change in position, or the displacement, over delta t. Delta r is a vector and delta t is a scalar. So when we get delta r over delta t, we got a vector. So the v is a vector, it has a direction, and it tells us about the direction of the displacement. So the direction of the velocity is the same as the direction of the displacement. So if we look here as an example in the figure, we have a leopard that is moving in a plane. So we chose the origin here. So here our reference point. Then we chose the x-axis as east direction, and we chose the y-axis as the north direction. So when the leopard goes east, he's going positive in the x direction, and when he goes north, he goes in the positive y direction. So the blue line indicates the path that the leopard takes, the motion of the leopard, or what we call the trajectory of motion. So if we take an initial point here, at this point, at t equal to 0 or t1, this is r0, and then we have r, which is r final, or r final here. The displacement vector is the line from r initial to r final. Then the average velocity is delta r over delta t. It's a vector, it has the same component, same direction as delta r. We can also divide this vector, the average velocity vector, into components. So instead of saying directly dr vector over delta t, I can say that the velocity has two components. A component on the x-axis, vx average, which is delta x over delta t, and then a component on the y-axis, which is vy average, which is delta y over delta t. The same as we defined it in one direction, but here we're defining it in two directions. Now the average speed, or the magnitude of the velocity, we can calculate it from the component as vx squared average, or vx average squared plus vy average squared, and then we take the square root. Now, if we want to know the instantaneous velocity, the velocity of the leopard or any object at a certain moment, what we do is we did the same as we did in one dimension. We take the limit as our interval become very, very small. So we define v, the instantaneous velocity at any time t, as delta r over delta t, but we do the limit as the time interval goes to 0. So we take much smaller time intervals until our time interval becomes 0. V is still a vector because delta r is still a vector. So we can still divide it into components, and we define Vx as the limit as delta t goes to 0 of delta x over delta t, and Vy as the limit of delta t goes to 0 of dy over delta t. However, here it's very important to look at it graphically. So if we look at the path of the leopard here, if we take we want to find the velocity v at the initial time. So we take first the first interval here. So this is the delta r. Now if we get closer, shorter time interval, we see we're getting t closer to t0. We're making our time interval much closer. Eventually, when delta t goes to 0, the line holding the vector v becomes the tangent to the trajectory. So the direction of the velocity at any time t is tangent to the trajectory of x function of y. This is different than what we did in the one dimension, where we draw x function of t. When we draw x function of t, the tangent is delta x over delta t, which give us the unit of velocity, which give us directly the slope of that tangent, directly give us the velocity. Here we're plotting x function of x. So the tangent, the slope of the tangent that we got, is not the value of the velocity. However, the tangent and the velocity have the same direction, because here we have distance x and distance y on our axes, not distance and time. And of course, if we want to look at the velocity of the magnitude of the velocity, we just do the sum square of the components, and we do the square root. Now, the same way, we have one more vector to define, which is the acceleration. So the acceleration is the rate of change of the velocity vector. Since now we know what is the definition of the velocity at any time t, if the velocity is changing, then we have an acceleration. And the average acceleration in any interval is the change in velocity vector over t, over delta t. Now, it's very important to point something out here. The change in velocity vector include the change in magnitude and in direction. So for a vector to be constant, it has to have both its magnitude and direction constant. Any change, either in magnitude or in direction, indicate a change in the vector. So if we have a change in the magnitude of the velocity or the speed, or a change in the direction of the velocity, then we have acceleration. And on average, the acceleration is delta v vector over delta t. If we want to define the instantaneous acceleration, we have to take the limit as delta t goes to 0. And of course, we can divide also our acceleration, since it's a vector, we can divide it into components, and we get the x component as delta v x over delta t, and the y component as delta v y over delta t. And to find the instantaneous component, we just do the limit. And also we can define the magnitude of the acceleration as ax squared plus ay squared, all together square root. Let's conclude this part of the lecture by a small example. So a circular racetrack with 250-meter radius lies in the plane and is centered at the origin. So here they already chose the reference point for us, which we're going to take it as the origin, and you have already the x-axis and the y-axis. And the racetrack has a radius from the origin 250 meters. So a car rounds the track counterclockwise, starting at a point 250 meter 0. So the object that we are studying is the car that's going around the track, and it's going counterclockwise. The starting point is r0, the initial position of the car. It has x equal 250 meters and y equal to 0, and that would be here. So that would be 250 from the origin on the x-axis and 0 on the y-axis. So these are x0 and y0. So we can write the initial position, and we can split it up into two components, x0 250 meters and y0 0 meters. Then we want to find the displacement after 1/4 lap. So after 1/4 means 1/4 of a lap, so it ends up here on the positive y-axis. So if I draw the final position. So the final position is its x component is 0 and the y component is 250 meters. So I can write it as 0 to 150 meters. So the displacement is the vector pointing from the initial position to the final position. If I draw the vector, the displacement vector, that would be the displacement vector. By definition, the displacement vector, delta r vector, is equal to r vector minus r0 vector. So it's the final position minus the initial position. I can split that into components, and I can draw these components on the figure as well. So I can draw the displacement on the x-axis. On the x-axis, the car goes from 250 to 0. And on the y-axis, it goes from 0 to 250. So I could write this also, the split, as delta x equal to x minus x0. Now, the x is 0 and x0 is 250, so we got minus 250 meters. So it's moving in the negative x direction. The y component is y minus y0, so it's 250 minus 0, it's plus 250. So it's moving in the negative x direction and in the positive y direction. Of course, that's on average for the first quarter of the lap. Now, the second part, tell us that the car travels at a constant speed and complete one lap in 100 seconds. Find its average velocity. So if the car completes one lap in 100 seconds, the time it takes to complete one quarter of the lap is 100 seconds over 4, because it's moving with a constant speed. So it needs 25 seconds. So the delta t of my trip, of this part of the trip, is 25 seconds. So the average velocity, I write the average velocity as v vector bar, which indicates that I'm talking about an average, is delta r over delta t. So I can also split that into two components. So I have Vx average, it's delta x over delta t. That's give us minus 10 meter per second. Vy average is delta y over delta t, which give us plus 10 meter per second. If I want to find the magnitude of the average velocity, here I have V average without a vector, so to indicate that's a magnitude, I just square the components and add the square of the components and then take the square root, and that gives me 14.1 meter per second. Thank you for listening, and I will see you soon, hopefully.